Drop a tiny speck of dust into this field and watch what happens to it. It doesn't just drift, it spins. And a little further over, another speck gets stretched apart like the space around it is leaking outward. Same field, two totally different fates, a couple inches apart. That's the thing that got me. A vector field looks like a boring lawn of arrows, right? Little arrows pointing wherever. But if you stop reading them as arrows and start reading them as water, as actual moving fluid, the whole picture wakes up. Every arrow becomes a current. And once it's a current, you can ask it questions a lawn of arrows can't answer. Is stuff piling up here or draining away? Is the flow twisting my speck of dust or carrying it straight? Those two questions have names, divergence and curl. And by the end of this, they're going to feel less like calculus and more like two dials. You can just read off the water. I got the mental picture wrong for years, honestly, so if it takes a second, you're in good company. Let's get the fluid moving first. Okay, let's make this concrete. A vector field just assigns an arrow to every point in space. At this point, the arrow points upright, medium length. At that point, it points down, really long. That's all it is, a rule. Give me a location. I'll give you a vector. The trick that makes it click is to say the vector isn't a static arrow. It's a velocity. It's telling you which way the water is moving right there and how fast. Long arrow, fast current. Short arrow, lazy trickle. So now the whole plane is a shallow pool, and every point has water sliding through it in some direction. Nothing is piling up yet. Nothing's spinning yet. We're just watching the flow exist. Keep your eye on the blue thing, this one little marker. I'm going to let go of it, and it's going to ride the current wherever the arrows push it. It traces out a path, and that path is called a streamline. Follow the arrows, you get the streamline. This is the whole game from here on out. We drop stuff in the water, and we watch how the water treats it. Here's the simplest interesting field. Every arrow points straight away from the center, and the further out you go, the longer the arrows get. If this is water, it's water gushing out of the origin in every direction. A spring, a faucet with no faucet, just a point where water appears out of nowhere and races outward. Now do the dust speck thing. I drop a marker anywhere, and it shoots away from the middle. Fine, expected. But watch what happens to a whole little blob of dust. Not one speck, a small circle of them. The circle rides outward, and as it goes, it grows. It gets bigger. The specks spread apart from each other because the arrows out front are longer than the arrows in back. So the front of the blob outruns the back. The blob is being stretched by the flow. That stretching, that expansion of a little region as it moves, that's the physical thing divergence measures, not the speed, the spreading, whether your patch of fluid is getting roomier or more crowded as it drifts along. So divergence is a number you attach to each point, and it answers one question. If I put a tiny circle of dust right here, does it expand, shrink, or stay the same size as the flow carries it? Positive divergence means expanding. Water is effectively being created at that point. It's a source. Stuff is flowing out faster than it flows in. Negative divergence, sometimes people call it convergence, means the circle shrinks. It's a sink, a drain, water disappearing down a hole. And zero divergence is the interesting boring case. The circle can move, it can even change shape, squish into an ellipse, but its area stays exactly the same. Nothing created, nothing destroyed. Here's the part I always forget and have to rederive. Divergence is completely local. It's not about the whole field. You could have arrows pointing every which way across the plane, and at one specific point the only question is what's happening in an infinitely tiny neighborhood right there. Zoom in far enough and you're just asking, in this speck of a region, is the water more crowded or less crowded a moment later? Let me push on this because sources and sinks are where it gets fun to just play. Picture a field with a source on the left, water pouring out, and a sink on the right, water draining in. In between, the flow bends from one to the other like the water's commuting across town. Now divergence lights up in exactly two places, bright positive at the source, bright negative at the sink, and basically nothing everywhere in the middle. Even though the water in the middle is clearly moving fast even, its divergence is zero, because a little blob passing through the middle doesn't grow or shrink, it just travels. This trips people up constantly. Motion is not divergence. You can have furious flow with zero divergence, and you can have divergence at a point where, on average, things feel weirdly still. Divergence isn't asking, is the water moving? It's asking, is the water appearing or disappearing? And in the real world, for regular incompressible water, it basically never appears or disappears, which means real water has zero divergence almost everywhere. And that fact turns out to run a shocking amount of physics. Alright, second dial. Forget the blob growing for a minute and put down something new. A tiny paddle wheel. Little cross with fins, free to spin around its center, but pinned in place so it can't drift. This is the single best tool in the whole subject, and it's basically a toy. Drop it in the outward gushing field from before. Does it spin? Water's flying past it, so you'd think yes. But no. The fins on the left get pushed out. The fins on the right get pushed out. It's symmetric, and the wheel just sits there. No rotation. Now drop the same paddle wheel into this field, where the arrows go around in circles. Obviously it spins. Great. But here's the one that broke my brain. This field where all the arrows point the same direction, to the right, but they're longer up top and shorter down low. Straight parallel flow. Nothing's curving. Drop the paddle wheel in. It spins. Because the fast water up top shoves the top fin harder than the slow water shoves the bottom fin. And the wheel torques around. Curl doesn't need circular arrows. It needs a difference across the wheel. So curl is the paddle wheel's answer. At every point you ask, if I pin a tiny wheel here, which way does it spin and how hard? Spin counterclockwise. We'll call that positive curl. Clockwise, negative. Wheel sits dead still, zero curl. And in 2 dimensions, that's the whole story. Curl is basically one number per point telling you the local twist. The shear example is the one to hold on to because it kills the obvious wrong intuition. Your gut says curl means the water goes in a circle. It doesn't. Curl means there's a mismatch in the flow across your little wheel, one side getting pushed more than the other, and that mismatch torques it. Straight line flow can have tons of curl. Circular flow can, believe it or not, have zero curl. If the speed drops off just right as you go outward, the wheel gets pushed forward on the inside and backward on the outside, and those cancel. I did not believe that the first time I saw it. We'll actually build that field in a bit because it's such a good gotcha. For now, curl is spin. Spin comes from difference, not from circles. Let's put the 2 dials side by side because the payoff is realizing they're independent. Divergence is the blob. Does my patch of dust grow or shrink? Curl is the paddle wheel. Does my patch of dust spin? And any point in any field has both readings, and they don't have to agree. Look at this. A field that's pure expansion, blob grows, wheel dead still. Divergence, yes. Curl, no. Now pure rotation, blob keeps its size. Wheel spins like crazy. Curl, yes. Divergence, no. Now a field that does both at once, water spiraling outward, like a drain running in reverse. The blob grows and the wheel spins. And finally the quiet one. Uniform, flow, everything sliding the same direction at the same speed. Blob unchanged, wheel unmoved, both zero. The water just goes. 2 questions, expand and spin, completely separate answers. If you remember nothing else, remember there are exactly 2 things you can ask a little patch of fluid, and these are them. Now, only now, let's let the symbols show up, because at this point they're just bookkeeping for stuff you already feel. Say the field pushes stuff with a horizontal part we'll call P, and a vertical part we'll call Q, both depending on where you are. Divergence measures spreading, so it asks, as I move right, does the rightward push P get stronger? That's the rate of change of P in the X direction. Plus, as I move up, does the upward push Q get stronger? Rate of change of Q and Y. Add those 2, that's divergence. Both are about a component growing in its own direction. That's what spreads the blob. Curl is the cross terms, the mismatches. How does the rightward push change as I move up versus how the upward push changes as I move right? Subtract them. If the top of my wheel is pushed right harder than the bottom, that's one term. If the right of my wheel is pushed up harder than the left, that's the other. The difference is the twist. That's it. Divergence adds the straight-on changes. Curl subtracts the crossed ones. Honestly, the notation is uglier than the idea, and I'm a little sorry about that on math's behalf. Okay, the gotcha I promised. This is the field where the arrows circle the origin, so it looks like a whirlpool, but the speed falls off as 1 over the distance, so the arrows get shorter fast as you go out. Every instinct says a paddle wheel dropped anywhere in a whirlpool must spin. Watch it. Away from the center, it doesn't. The wheel rides all the way around the origin, its center orbits, but the wheel itself never turns relative to the room, and the reason is beautiful. The inner fin sits in fast water, pushing it one way around. The outer fin sits in slow water, and the drop-off is tuned so precisely that the forward shove on the inside exactly cancels the backward drag on the outside. Net twist, 0. Curl equals 0 everywhere except one place, the origin. Right at the center where all that circulation is coming from, curl blows up, it's a spike, infinite in the idealized version. So the whole whirlpool's rotation is secretly crammed into a single point, and the entire rest of the field is technically curl-free. This is the exact math behind why you can have a vortex line in air with still, non-spinning fluid all around it. I stared at this for an embarrassingly long time. Here's where this stops being a math curiosity and starts running the world. Take Maxwell's equations, the 4 lines that describe all of electricity and magnetism. 2 of them are literally divergent statements, and 2 are curl statements. The divergence of the electric field tells you where charge is. Charges are the sources, the little faucets the field gushes out of. The divergence of the magnetic field is 0, always, everywhere. And that single fact is the entire reason there's no such thing as a magnetic monopole, no isolated North Pole, because 0 divergence means no sources, no faucets, nothing for the field to gush out of. And the curl equations say a changing magnetic field twists up an electric one and vice versa, which is, no exaggeration, light. That mutual twisting propagating through space is a radio wave, is the glow off your screen right now. Same 2 dials. In fluid dynamics, 0 divergence is what incompressible means, and curl is vorticity, the thing that makes airplane wings work and hurricanes spin. You learn 2 questions to ask a patch of water, and it turns out physics only ever asks those 2 questions. So that's the pair. Divergence, the blob that grows or shrinks. Curl, the paddle wheel that spins or doesn't. 2 little machines you can drop into any field to read it off by hand. No equations required, though the equations are right there when you want them. And here's the thread I want to leave you tugging on, because it still bugs me. We found a field, the whirlpool one, where the curl was 0 absolutely everywhere, except a single point you're not allowed to visit. And the field genuinely circulates. Water goes around. You can measure it going around. So there's this gap between what's happening locally, curl is 0, the wheel doesn't turn, and what's happening globally, stuff clearly loops. How do those 2 facts live together? The answer is one of the prettiest theorems in all of math. It's called Stokes' theorem, and it says the total spin inside a loop equals the flow measured around its edge, which means that one forbidden point at the center can secretly control the entire boundary. But that's a whole other video. Go drop some paddle wheels in your head for a while first.